Section 1 Introduction. In this introduction, we discuss the use of reinforcement learning from human feedback, RLHF, to improve the performance of large language models, LLMs. RLHF is a method that uses human feedback to fine-tune these models, making them more aligned with human preferences. This process involves using an RL algorithm, such as PPO, to optimize the model. However, this method relies heavily on a reward model that is based on human-labeled preferences. Gathering this data can be costly and time-consuming. To overcome this challenge, other methods have been proposed that don't require human annotation. These include reinforcement learning from AI feedback, RLAIF, and context distillation. RLAIF uses an LLM to simulate human preferences, but this can result in noisier data. This issue is further compounded when the same prompt is used to generate both outputs, making them hard to differentiate. Context distillation, on the other hand, modifies the initial prompt to create more training signal. However, this method only generates a single output per prompt, which is then used for supervised fine-tuning. This loses the pairwise preferences that help RLHF-style approaches to derive signal from the contrast between outputs. We believe that combining the advantages of both RLAIF and context distillation could be more effective. To this end, we propose reinforcement learning from contrast distillation, RLCD. This method generates preference data by creating two variations of a prompt: a positive prompt that encourages a change towards a desired attribute, and a negative prompt that encourages a change against it. We then generate model outputs for each prompt and automatically label the output from the positive prompt as preferred. This way, RLCD automatically generates pairwise preference labels. Compared to RLAIF, RLCD typically results in a clearer difference in the quality of the outputs, which may result in less label noise. Compared to standard context distillation methods, RLCD can derive signal not only from the positive prompt, which improves output quality, but also from the negative prompt, which degrades it. We tested the effectiveness of RLCD through human and automatic evaluations on 3 tasks, aiming to improve the ability of Llama 7B to generate harmless outputs, helpful outputs, and high-quality story outlines. Our results show that RLCD significantly outperforms both RLAIF and context distillation baselines in pairwise comparisons when simulating preference data with Llama 7B, while still performing equal or better when simulating with Llama 30B. We plan to release all code at a later date, but RLCD is fairly easy to implement by modifying any reference RLAIF codebase. Section Summary. Reinforcement learning from human feedback, RLHF, aligns language models with human preferences, but collecting high-quality pairwise preference data is expensive. To address this, approaches like reinforcement learning from AI feedback, RLAIF, and context distillation have been proposed, but they have limitations. To overcome these limitations, we propose reinforcement learning from contrast distillation, RLCD, which combines the advantages of both approaches. RLCD generates preference data by creating positive and negative prompts that encourage directional attribute change in the model outputs, resulting in clearer differences in output quality and less label noise. RLCD outperforms RLAIF and context distillation in pairwise comparisons and is easy to implement. Section 2 Related work. In recent times, we've seen a surge in the use of reinforcement learning, RL, methods that utilize reward models trained on human preferences to align powerful pre-trained language learning models, LLMs. However, gathering human pairwise preferences can be quite costly. One approach to this is reinforcement learning from AI feedback, RLAIF, which uses an LLM to simulate human pairwise preferences. This could be the same LLM that will be aligned later, or a more powerful LLM acting as a guide. Typically, these methods get pairwise preferences by comparing the scores of 2 independently and identically distributed outputs, denoted as O_1, O_2. Our method, reinforcement learning from contrast distillation, RLCD, takes a different approach. Instead of comparing 2 similar outputs, RLCD generates outputs from different distributions, eliminating the need for after-the-fact scoring, whether by humans or AI. RLCD is related to context distillation methods, which create data for supervised fine-tuning by prompting a language model with different contexts. Unlike knowledge distillation methods that use more powerful models as teachers, context distillation methods often generate data using the same LLM that will be aligned or fine-tuned later. We specifically apply this approach to align a model we call Llama 65B. Unlike existing context distillation methods, RLCD generates pairwise preference data to train a preference model, and then applies RL. As a result, RLCD can extract a training signal from the contrast in output distributions for two different context-modified prompts, denoted as P_+ and P_. We've found that using a contrastive loss in RL can be very effective. Traditional reward signals can sometimes result in insufficient numerical differences between good and bad cases. Contrastive loss, on the other hand, naturally focuses on sample pairs that look similar but have different underlying meanings with current representations. This improves both sample efficiency and model quality. RLCD uses this idea to enhance the generation of simulated preference data in the RLHF pipeline. We now present our method, RLCD, a new way to simulate the initial pairwise preference data in an RLHF pipeline without needing a more powerful Oracle LLM. Section summary. In recent work, RL approaches have been used to align strong pre-trained language models, LLMs, by leveraging reward models trained on human preferences. However, collecting human pairwise preferences can be expensive. To address this, RLCD, reinforcement learning from contrast distillation, simulates human pairwise preferences using a LLM, eliminating the need for post-hoc scoring. RLCD is related to context distillation approaches, but instead of using stronger models as teachers, it generates pairwise preference data to train a preference model followed by applying RL. By using a contrastive loss, RLCD improves the generation of simulated preference data in the RLHF pipeline. Section 3.1 Method Description. Our method, RLCD, starts with an initial unaligned language model and a set of prompts. These prompts serve as the starting points for generating data on pairwise preferences, a process similar to what is done in RLHF or RLAIF. For each prompt, we create two versions, one that encourages a change towards the attribute we're interested in, like harmlessness or helpfulness, and another that encourages a change against it. We'll call these the positive and negative prompts. When these prompts are fed into the original language model, they produce corresponding outputs. We then pair these outputs, automatically, labeling the output from the positive prompt as the preferred one. Once we have these pairs, we follow the standard RLHF process. We train a preference model on the simulated pairwise preferences, derive a reward model from the preference model, and use this reward model to align the original language model. Implementing RLCD is straightforward if you're starting from an existing RLAIF workflow. The main decision to make is how to construct the positive and negative prompts for generating preference pairs. We suggest two main criteria for selecting these prompts. 1. The positive prompt should be more likely than the negative one to produce outputs that exemplify the desired attribute. Alternatively, the negative prompt could explicitly encourage a change towards the opposite attribute. 2. The positive and negative prompts should be as similar as possible in form. For example, they might only differ in the words harmless versus harmful. The first criterion is pretty obvious. The second one is to avoid introducing biases that aren't related to the attribute we're interested in. Essentially, the positive and negative prompts create two different distributions. The first criterion ensures that these distributions differ as much as possible in the desired attribute, while the second criterion ensures that they differ as little as possible in other ways. In our experiments, we found that RLCD is very good at amplifying the contrast between the positive and negative prompts, compared to other methods using similar prompts. So when you're creating these prompts in practice, it might be more worthwhile to focus on the second criterion. For example, you could just write a short description in parentheses to create the positive and negative prompts. Section summary. RLCD is a method that uses an initial unaligned language model, LLM, and prompts to generate pairwise preference data. It constructs positive and negative prompts that encourage a directional change towards or against the attribute of interest. RLCD then trains a preference model on the generated pairwise preferences and derives a reward model to align the original LLM. The choice of positive and negative prompts is important, with the main criteria being that the positive prompt should be more likely to produce outputs exemplifying the desired attribute, while the surface forms of the positive and negative prompts should be as similar as possible to avoid unintended biases. Section 3.3 Intuitions for RLCD. We'd like to delve into the reasons why the data generation method of RLCD, reinforcement learning with context distillation, might be more favorable than the similar previous method, RLAIF, reinforcement learning with attribute inference. The primary reason is that RLAIF produces two independent and identically distributed I/D outputs, labeled as O_1 and O_2. In many instances, these outputs may not differ significantly in the attribute of interest, leading to a low signal-to-noise ratio. To put it another way, It might seem strange to rearrange I.D. outputs from a generic prompt, rather than generating outputs from a more specific prompt. For example, in a case we've outlined in table label, tab, RLAIF_bad_ example, both RLAIF outputs, O_1 and O_2, assist a human in achieving an unethical goal. It's unclear which output is better. However, in our data generation using the Llama 7B model, O_2 is preferred by a small margin at the 60th percentile of label polarity. While classification models usually benefit from training examples close to the decision boundary, the issue with RLAIF is that these examples are not labeled by humans and can therefore be extremely noisy. It might even be better to avoid such examples if we can't label them accurately. In contrast, RLCD creates a pair of outputs, O_+ and O_, which are more likely to differ on a specific attribute. This difference is evident in table label, tab, RLAIF_bad_ example, where O_+ is clearly more ethical than O_. Although RLCD's outputs can also be noisy, they tend to be more distinct on average than RLAIF's, leading to more accurate labels. Additionally, RLAIF's post hoc scoring requires both outputs, O_1 and O_2, to be placed in the context window of the scoring language model, necessitating a longer effective context window. This scoring step might also add some extra computational cost compared to RLCD. Therefore, RLCD might be a better choice when dealing with longer outputs, even when using cutting-edge language models with context windows of tens of thousands of tokens. These models are not only costly to run but may also struggle to pay attention to certain parts of their context window. Section summary. RLCD is preferred over RLAIF because RLCD generates outputs that are more likely to differ on a specified attribute, resulting in more accurate labels. Additionally, RLCD is more efficient than RLAIF when dealing with longer form outputs, as it does not require the model to have a longer effective context window and imposes less compute cost. Section 4 Experiments. We're now going to assess how well RLCD performs in real-world scenarios. We've chosen 3 tasks for this, each with a different set of prompts. 1. Harmlessness prompts. These are dialogues that often contain offensive or inappropriate text. The aim here is to generate responses that are socially acceptable, ethical, and non-offensive, even when the context is toxic. Additionally, the responses should still be useful and relevant to the conversation, rather than generic responses like, "thank you," or "sorry." 2. Helpfulness prompts. These are dialogues where the human participant is usually seeking information or advice. The goal here is to generate responses that are helpful. 3. Outlining prompts. These are dialogues where the human participant provides a story premise and asks for an outline. The goal here is to create a well-structured and interesting story outline based on the given premise. We've designed all prompts to generate the next assistant response at some point in the ongoing human-assistant conversation. We've drawn inspiration from previous work for our harmlessness and helpfulness prompts, and we've used their training sets to create the initial prompts for preference data simulation. Each training set contains just over 40,000 conversations. We've also included the outlining prompt set because we believe it requires more long-range planning, as well as the ability to combine multiple different attributes like interestingness, well-formatedness, and relevance to the premise. For these prompts, we've used 40,000 existing premises from the internet, and assistant responses automatically start with, "Here is a possible outline, NN1." To encourage correct basic formatting. For the harmlessness task, we've written 16 pairs of context phrases for constructing positive and negative prompts. For helpfulness, we've used just one phrase pair, asking for helpful or unhelpful responses. For outlining, we've used 3 phrase pairs, designed to contrast interestingness, well-formatedness, and premise relevance. We've run 2 variations of RLCD for each task, simulating preference data using the base Llama 7B and Llama 30B models. We've used the base Llama 7B as the initial model to be aligned via RLCD, regardless of the model used in preference data simulation. We've compared RLCD to 3 baselines, Llama, RLAIF, and Context Dist. For each task, we've run pairwise evaluations for RLCD compared to each baseline. We've measured both harmlessness and helpfulness for the harmlessness task. For the helpfulness and outlining tasks, we've collected one set of labels for overall helpfulness and outline quality, respectively. For each pairwise evaluation, we've asked humans to compare 200 examples on a scale from 1, output A is much better, to 8, output B is much better. We've also asked GPT-4 for binary judgments on 1,000 examples. The results show that RLCD outperforms all of our baselines according to both human and GPT-4 evaluations. On harmlessness prompts, RLCD is better on the main harmlessness metric, while not sacrificing helpfulness compared to baselines. RLCD is also much better than baselines on helpfulness by itself, as well as the somewhat more complex task of story outlining. The gap between RLCD and all baselines is especially large when using Llama 7B for preference data simulation. Even our strongest baseline, RLAIF, comes close to RLCD only at 30B model scale for data simulation, while substantially underperforming at 7B model scale. Section Summary. In this section, the authors describe the experiments conducted to evaluate the effectiveness of RLCD. They run experiments on 3 different tasks: harmlessness prompts, helpfulness prompts, and outlining prompts. RLCD is compared to 3 baselines: Llama, RLAIF, and Context Dist, and it outperforms all of them according to both human and GPT-4 evaluations. The results show that RLCD is better in terms of harmlessness, helpfulness, and story outlining, even at smaller model scales. Section 5 Analysis. In our analysis section, we conducted 2 more studies to gain a deeper understanding of RLCD. Moving on to the discussion, we introduced RLCD in this paper, a technique for aligning language learning models, LLMs, using simulated pairwise preference data derived from the same LLM. RLCD's approach is similar to RLAIF's, but it incorporates elements of context distillation. We generate simulated pairwise preference data using a positive prompt and a negative prompt, with the goal of enhancing the difference between the positive and negative outputs. We do this by promoting changes in opposite directions on a desired attribute, such as harmlessness. Our empirical findings from 3 different alignment tasks across various model scales for preference data simulation support our belief that RLCD can be highly effective. It outperforms both RLAIF and context distillation baselines. However, despite our compelling empirical evidence, we believe that RLCD only begins to explore the potential of modifying the automatic preference data simulation process for RLHF pipelines. For example, in the various experimental settings in this study, our current RLCD approach benefits from intuitively pushing the positive and negative outputs further apart to decrease label noise. In situations where it's easy to re-rank outputs after the fact, or where there's a sufficiently robust scoring LLM to provide accurate labels even near the classification boundary, one could try to create more challenging training examples by intentionally pushing the positive and negative outputs closer together compared to what RLAIF achieves by chance. Furthermore, it might be beneficial to simulate preference labels in formats other than a single binary label. This could be done by ranking more than 2 outputs at a time or using more detailed annotations on longer outputs. We're eager to explore these and other opportunities to continue improving automatic data simulation procedures for LLM alignment. Section Summary. In this section, the authors present RLCD, a method for aligning LLMs using simulated pairwise preference data. RLCD aims to amplify the difference between outputs by encouraging opposite directional changes on a desired attribute. Empirical results show that RLCD outperforms both RLAIF and context distillation baselines, but the authors believe there is still room for improvement in modifying the automatic preference data simulation procedure for RLHF pipelines, such as creating harder training examples or using more fine-grained annotations.